When people say the Milky Way is large, they usually mean it in a vague and comfortable way, as if large were enough to describe what kind of structure we actually live inside. But the problem is that ordinary language breaks down very quickly once you try to apply it to a galaxy, because the Milky Way is not merely a large collection of stars in the same way a forest is a large collection of trees. It is a gravitational system on a scale so extreme that the numbers stop behaving like real experience and start behaving like abstractions. And yet those abstractions describe the place that contains every naked eye star you have ever seen in the night sky. The Milky Way stretches roughly 100,000 light years across, which means that even light moving at the fastest speed the universe allows would need 100,000 years to cross it from one side to the other. And inside that disk, there are somewhere between 100 billion and 400 billion stars, perhaps more, depending on how the faintest populations are counted, all embedded in a larger halo of dark matter whose mass outweighs the visible galaxy by a wide margin. This is not an isolated object in empty space. And it is not a simple wheel of stars either. It is a barred spiral galaxy with a central bulge, spiral arms, rich in gas, and young stars, older stellar populations distributed more broadly, and a hidden gravitational framework that holds the whole structure together. What makes this more interesting is that we are not standing outside it, looking in, we are inside it, trying to infer the shape of the system from a position buried within one of its minor structures. Our sun sits about 26,000 light years from the galactic center in a smaller feature called the Orion Spur, between the larger Sagittarius and Perseus arms, which means we do not occupy the dramatic center of the galaxy, and we do not sit near its outermost edge either. We live in a fairly ordinary region, one that turns out to be quiet enough for planetary stability and long biological evolution. And that matters because galaxies are not equally friendly in all locations. Closer to the center, stars are more densely packed, radiation environments are harsher, and gravitational disturbances are more common. Out in the thin outskirts, the raw materials for star and planet formation become more sparse. Our position is not central, but it is workable, and that may be far more important. The Milky Way also deserves to be called exceptional in a statistical sense, which is something people often miss. When you hear about galaxies, the imagination tends to jump toward the most spectacular giants, the monstrous ellipticals and oversized spirals that dominate astronomy images and popular science headlines. But those are not the norm. Most galaxies in the universe are dwarf galaxies, faint systems containing a few billion stars or less, often only a tiny fraction of the Milky Way in both diameter and mass. Against that background, our galaxy is not average at all. It is one of the larger galaxies in the observable universe, comfortably above the vast majority of systems astronomers detect. It is not the largest, and it is not rare in the sense of being unique, but it is unquestionably substantial. If you rank galaxies by size or stellar mass, the Milky Way would sit far above the crowded lower range where most galaxies spend their existence. That matters. Because scale changes interpretation, a galaxy with hundreds of billions of stars is not just bigger than a dwarf by a factor you can state on paper. It has a different history, a different gravitational influence, a different ability to retain gas, build structure, and support long-term star formation. The Milky Way has had enough mass to remain dynamically important in its local environment, enough material to produce generations of stars over billions of years, and enough internal stability for complex systems like our own solar system to emerge inside it. Those are not minor details. They are features of a very large galaxy, So before comparing the Milky Way to larger cosmic structures or to the most extreme galaxies ever observed, it is worth being precise about this first point. By the standards of galaxies themselves, our home is already an unusually large system. And that fact stands on its own without needing exaggeration. If you stay inside the Milky Way, it is easy to treat it as a complete system, something that feels self-contained simply because everything you can see appears to belong to it. But that impression begins to change the moment you step outside the boundary of our own galaxy and start placing it next to others, not in isolation but in context, because the Milky Way is not alone, and it was never alone. The nearest large galaxy to us is the Andromeda Galaxy, sitting about 2.5 million light years away, close enough in cosmic terms that its light has been reaching Earth since long before humans existed, and large enough that when you compare the two directly, it quietly challenges the assumption that our galaxy sits at the top of anything. Andromeda is wider, more massive, and contains roughly 1 trillion stars, more than double most estimates for the Milky Way, and it is not drifting aimlessly through space, but moving toward us, pulled by mutual gravity in a slow, inevitable approach that will eventually lead to a merger billions of years from now, not a violent collision of stars, but a gradual restructuring of both galaxies into something new. Andromeda is not the only neighbor. Surrounding the Milky Way are smaller companions, including the Large Magellanic Cloud and the Small Magellanic Cloud, irregular galaxies that orbit our own and contain billions of stars each. Visible from the southern hemisphere as faint, cloud-like patches in the sky long before anyone understood what they were. Beyond these, there are dozens of dwarf galaxies, faint systems that are gravitationally bound to the Milky Way, some stretched and distorted as they are slowly pulled apart, their stars being absorbed over time into the larger structure. When you take all of these together, the Milky Way, Andromeda, Triangulum, and roughly 50 smaller galaxies, you get what astronomers call the local group, a region of space about 10 million light years across that functions as our immediate cosmic neighborhood. At first glance, the local group still feels manageable, almost like a scaled-up version of something familiar, a loose gathering of galaxies rather than an overwhelming structure. And within it, the Milky Way does not disappear into insignificance. It remains one of the dominant members, second only to Andromeda in size and mass, which might suggest that our earlier sense of scale still holds, that we are living inside something large and relatively important, but the shift begins not by removing that status entirely, but by reframing it. Being large inside a small group is not the same as being large in any absolute sense. And the local group itself is not a special region of the universe. It is simply one of countless similar collections scattered across cosmic space, most of them containing a few large galaxies surrounded by many smaller ones, arranged in patterns that repeat again and again with slight variations. This is where perspective starts to move, not abruptly but steadily. The Milky Way does not shrink in any physical way. It remains exactly what it was in the previous view, a massive spiral galaxy with hundreds of billions of stars. But its position changes the moment you place it alongside something like Andromeda and then embed both of them within a broader system. That is itself just one example among many. What once felt like a central structure begins to look more like a member, still significant within its immediate surroundings, but no longer defining the scale of those surroundings. The local group does not revolve around the Milky Way, and it does not need to, because the structure exists independently of any single galaxy within it. Nothing about this comparison requires exaggeration or dramatic interpretation, The numbers are straightforward. The distances are measurable, and the relationships are well understood. The Milky Way is large, Andromeda is larger, and both are part of a group that is modest when compared to the broader distribution of galaxies across the universe. The shift in perspective comes from placing these facts side by side rather than treating them separately. Because once they are viewed together, the idea of our galaxy as a complete or dominant frame of reference becomes harder to maintain without qualification. The local group feels substantial only until you place it inside something larger, and that transition does not require speculation or imagination so much as it requires extending the same logic. One step further, because just as galaxies gather into groups, those groups do not exist in isolation either. They are embedded within far bigger structures known as superclusters. Vast regions where gravity has drawn together not just individual galaxies, but entire collections of them into loose. Sprawling systems that stretch across tens or even hundreds of millions of light years. Our local group, along with many other nearby groups and clusters, belongs to what has traditionally been called the Virgo supercluster, a massive structure centered around the Virgo cluster, which itself contains thousands of galaxies, many of them larger and more massive than anything in our immediate neighborhood. And already at this level, the scale begins to shift in a way that is difficult to ignore, because what once felt like a complete environment now becomes a small component inside something that does not organize itself around us at all. The Virgo supercluster spans over 100 million light years, a scale that makes the 10 million light year width of the local group seem limited rather than expansive. And within this larger structure, our galaxy is not a dominant feature, but simply one member among many located in a relatively quiet outer region rather than near the dense central areas where galaxies crowd together and interactions become more frequent. The gravitational center of this system is not the Milky Way nor Andromeda, but regions like the Virgo cluster itself, where mass is concentrated on a much larger scale, and this redistribution of importance happens naturally once the boundaries expand, not because anything about the Milky Way has changed, but because the frame of reference has widened beyond the scale where our galaxy can define it. Even this description, however, turns out to be incomplete. In 2014, astronomers refined this picture by identifying an even larger structure that redefines how we understand our position, a supercluster of superclusters known as Laniakea supercluster, a name derived from Hawaiian meaning immeasurable heaven, which reflects not just its size, but the difficulty of grasping it in concrete terms. Laniakea spans roughly 520 million light years and contains on the order of 100,000 galaxies, including the entire Virgo supercluster as just one region within it. And what defines Laniakea is not simply proximity but motion, because all of the galaxies within this vast structure, including the Milky Way, are moving in a coordinated way toward a common gravitational region, often referred to as the Great Attractor, a point in space obscured by the plane of our own galaxy, but detectable through its influence on the motion of galaxies across a wide area. This is where the shift becomes more than just a change in scale and turns into a change in interpretation. The Milky Way is not stationary within this framework. It is part of a large-scale flow, one element in a gravitational system that extends far beyond anything visible in the night sky. And the idea of our galaxy as a central or defining structure becomes increasingly difficult to maintain, not because it lacks size or complexity, but because it is embedded within patterns that operate independently of it. The local group moves. The Virgo supercluster participates in that motion, and Laniakea itself is part of an even broader distribution of matter, suggesting that structure in the universe is layered in a way that consistently removes any single galaxy from a position of dominance once the boundaries are expanded. At this scale, comparisons begin to lose their intuitive meaning. Distances measured in hundreds of millions of light years do not translate into visual images easily. And the relationships between structures are understood more through mapping in motion than through direct observation. The Milky Way remains what it was, a large spiral galaxy with hundreds of billions of stars, but its role within these larger systems is defined by inclusion rather than influence. It belongs to the local group, which belongs to the Virgo supercluster, which belongs to Laniakea, and each step outward reduces the extent to which our galaxy can be treated as a reference point for anything beyond its immediate surrounding. Nothing in this process diminishes the physical reality of the Milky Way itself, but it does change how its importance is framed, because once it is placed within structures that extend hundreds of millions of light years and contain tens of thousands of galaxies, it becomes clear that its scale, while large in isolation, is not sufficient to anchor the hierarchy it exists within. Even structures as large as Laniakea do not exist in isolation. And the moment you extend the same line of reasoning outward again, the pattern begins to reveal itself in a way that is less about individual objects and more about the architecture that connects them. Because when astronomers map the positions of galaxies across vast distances, they do not find a uniform distribution nor a random scattering, but something far more organized, a network of filaments, clusters, and empty regions that together form what is known as the cosmic web, a structure so large that it cannot be understood by looking at any single part of it, only by stepping back far enough to see how everything fits together. In this framework, galaxies are not the primary units of structure in the way we might first imagine. They are more like nodes, embedded within a larger system defined primarily by dark matter, an invisible component that does not emit or absorb light, but whose gravitational influence shapes the distribution of everything else. The visible matter, the stars, gas, and dust that make up galaxies like the Milky Way, collects along these dark matter filaments, tracing out a pattern that extends across hundreds of millions and even billions of light years, forming long chains and walls of galaxies separated by vast voids where very little matter exists at all. These voids are not small gaps. They are enormous regions, sometimes hundreds of millions or even billions of light years across, where the density of galaxies drops dramatically, creating a contrast between dense filaments and nearly empty expanses that defines the large-scale structure of the universe. One of the most striking examples of this structure is the Sloan Great Wall, a massive sheet of galaxies stretching over 1 billion light years across, containing tens of thousands of galaxies arranged in a relatively thin but extraordinarily extended formation. And even this is not the largest known structure, because beyond it lies the Hercules Corona Borealis Great Wall, an immense filament of galaxy clusters spanning on the order of 10 billion light years, a scale so extreme that it approaches the size of the observable universe itself and challenges the limits of our current models of cosmic evolution. These structures are not isolated anomalies, but part of a broader pattern, one that emerges naturally from the way matter has evolved under gravity since the early universe, where tiny fluctuations in density grew over billions of years into the vast network we observe today. The observable universe, the region of space from which light has had time to reach us since the beginning of cosmic expansion, spans roughly 93 billion light years in diameter, a figure that already exceeds intuitive expectations given the universe's age of about 8 billion years, because space itself has been expanding, stretching the distances between galaxies as light travels through it. Within this observable volume, astronomers estimate there are on the order of 2 trillion galaxies, each embedded within the cosmic web, each participating in this larger structure, whether or not it is immediately apparent from a local perspective. The Milky Way, along with the local group, the Virgo supercluster, and Laniakea, occupies a small region within this network, located along one of its filaments, connected gravitationally to other systems, but not in any way defining the structure as a whole. At this level, the idea of centrality becomes difficult to apply in any meaningful sense. The cosmic web has no center in the way smaller systems do, no single point from which everything radiates, and no preferred location that could reasonably be described as more fundamental than another. Instead, it is a distributed structure shaped by the underlying distribution of dark matter and the expansion of space, where local groupings emerge naturally but do not extend their influence across the entire system. The Milky Way is part of this network in exactly the same way as countless other galaxies, occupying one position among many, following the same physical law, and contributing to a pattern that is defined collectively rather than individually. Understanding this structure does not require imagining the entire universe at once, which would be impractical, but it does require accepting that the scale at which meaningful organization occurs is far larger than any single galaxy or even any single supercluster, and that the patterns governing the universe operate across distances that extend well beyond the range where familiar comparisons remain useful. Once the large-scale structure of the universe is understood, the next step is not to move outward again, but to look more carefully at the galaxies themselves, because one of the easiest mistakes to make is to assume that all galaxies resemble the Milky Way in size, structure, or behavior, when in reality the range of variation is far broader than intuition suggests. And it is only by placing our galaxy within that full range that its true position becomes clear. Galaxies are typically classified into spirals, ellipticals, and irregulars, but these categories only describe shape, not scale, and within each category there exists an enormous spread in size, mass, brightness, and evolutionary history that makes direct comparison less straightforward than it first appears. At one extreme, there are dwarf galaxies, which are by far the most common type in the universe. Small systems containing anywhere from a few million to a few billion stars, often only a few thousand light years across, faint and difficult to observe unless they are relatively close, and yet numerous enough that they dominate galaxy counts in almost every survey. These dwarfs are not merely smaller versions of larger galaxies. They are often structurally simpler, more easily disrupted, and in many cases they exist as satellites orbiting larger systems, including the Milky Way itself, which is surrounded by dozens of such companions, some of them in the process of being gradually absorbed through tidal interactions. Against this background, the Milky Way stands out immediately, not because it is unusual in form, but because it is large in a statistical sense, containing hundreds of billions of stars and spanning about 100,000 light years, placing it well above the majority of galaxies in both mass and size. At the other extreme, however, are the giant and supergiant galaxies, systems that push the upper limits of what galaxy formation can produce, including massive ellipticals like IC 1000, 101, which extends several million light years across and contains on the order of 100 trillion stars, far exceeding the Milky Way in both physical size and stellar population. And cluster-dominant galaxies such as Messier 87, whose mass, including its dark matter halo, outweighs our galaxy by a substantial margin, and whose central black hole alone contains billions of solar masses, orders of magnitude larger than the black hole at the center of the Milky Way. These systems are not representative of typical galaxies, but they demonstrate the upper bound of galactic growth, often having formed through repeated mergers and accretion over billions of years in dense cluster environments where interactions are frequent and sustained. Between these extremes lies a wide spectrum of intermediate systems, including spiral galaxies larger than the Milky Way, such as low-surface brightness giants that spread their stars across vast areas, as well as smaller spirals and irregular galaxies with varying levels of star formation activity and structural coherence. The Milky Way fits within this middle to upper range, not at the absolute top, but clearly above average, a large spiral galaxy that has maintained a steady rate of star formation, avoided major disruptive events in recent cosmic time, and retained enough gas to continue evolving in a relatively stable manner. This stability is not a trivial feature, because many of the most extreme galaxies are also the most chaotic, with intense bursts of star formation, active galactic nuclei, and environments that are far less conducive to the long-term development of planetary systems like our own. What emerges from this comparison is not a simple ranking, but a distribution where the Milky Way occupies a position that is simultaneously unremarkable in type and notable in scale, a galaxy that does not exhibit the extreme properties of the largest ellipticals or the smallest dwarfs, but instead sits in a region of parameter space that is both common enough to be understood and large enough to stand out statistically. If one were to select galaxies at random from across the observable universe, the majority would be smaller than the Milky Way, many by large factors, while only a small fraction would exceed it in size or mass, and an even smaller fraction would do so dramatically. This duality is important because it prevents a misleading conclusion in either direction. The Milky Way is not among the largest galaxies ever observed, and it is clearly surpassed by systems that dominate cluster centers. But it is also not a typical galaxy in the sense of representing the median of the distribution, which is skewed heavily toward much smaller systems. Its true rank is therefore relative, defined not by a single comparison, but by its position within a broad spectrum that includes both far smaller and far larger galaxies, each shaped by different formation histories and environmental conditions. Understanding the Milky Way as it exists today requires stepping back into a much earlier phase of the universe, because galaxies are not static structures that appeared fully formed. They are the result of a long process that began shortly after the Big Bang, when matter was distributed almost uniformly with only tiny variations in density, fluctuations so small that they would have been invisible without precise measurement. And yet over billions of years, those slight differences were amplified by gravity, drawing matter inward to form the first small concentrations of dark matter and gas, structures that would eventually become the seeds of galaxies. The earliest galaxies were not large systems like the Milky Way, but small, irregular collections of stars forming within dark matter halos, merging repeatedly as gravity pulled them together, gradually building more massive and complex systems through a process that never truly stops, only slows as the universe expands and distances between structures increase. The Milky Way formed through this accumulation, not in a single event, but through a sequence of mergers and accretion episodes that assembled its mass over more than 10 billion years. And this history is still visible today in the distribution and composition of its stars, because different populations carry chemical signatures that reflect the environments in which they formed, allowing astronomers to trace back the origins of various stellar groups to smaller galaxies that were absorbed long ago. This process continues even now, albeit at a reduced pace, as dwarf galaxies orbiting the Milky Way are gradually disrupted and incorporated into its halo. Their stars stretched into streams that wrap around the galaxy and slowly disperse. The Milky Way is therefore not a single coherent object in the strictest sense, but a composite structure, the product of many smaller systems that have merged over cosmic time. At the same time, the Milky Way is not stationary within the larger structures described earlier. It is moving through space as part of the local group, influenced by the gravitational pull of nearby galaxies and the broader motion of the Laniakea supercluster toward the region known as the Great Attractor, a flow that reflects the distribution of mass on scales far larger than any individual galaxy. This motion is not directly perceptible in everyday terms, but it is measurable. With our galaxy traveling at hundreds of kilometers per second relative to the cosmic microwave background, indicating that even on large scales, galaxies are not fixed points, but participants in ongoing dynamical processes that connect them to structures far beyond their immediate surroundings. Looking forward, the most significant event in the Milky Way's future is its interaction with the Andromeda Galaxy, which is approaching at a speed of roughly 100 kilometers per second and is expected to merge with our galaxy in about 4 to 5 billion years. This encounter will not resemble a collision in the everyday sense, because the distances between stars are so large that direct stellar impacts will be rare. But the gravitational interaction will profoundly reshape both galaxies, distorting their spiral structures, redistributing their stars, and eventually forming a single, larger elliptical galaxy. Simulations suggest that this process will take several billion years to complete, during which the two galaxies will pass through each other multiple times before settling into a stable configuration. Likely containing on the order of 1.5 trillion stars. Beyond this merger, the long-term future of the Milky Way is tied to the expansion of the universe, which is accelerating due to dark energy. As space continues to expand, distant galaxies will recede beyond the observable horizon, their light no longer able to reach us. And over tens of billions of years, the visible universe from within the merged Milky Way Andromeda system will become increasingly empty, with only the remnants of the local group remaining gravitationally bound. This isolation is not a temporary condition, but a consequence of cosmic expansion, effectively separating structures that are not strongly bound by gravity and leaving behind islands of matter surrounded by vast, unobservable regions. None of these processes alter the current state of the Milky Way in any immediate sense, but they define its trajectory within a universe that is constantly evolving, where formation, motion, and eventual transformation are not exceptional events, but fundamental aspects of how structure develops over time. Once the scale of the universe is laid out in full, from galaxies to superclusters to the cosmic web and beyond, the question that remains is not about structure, but about significance, because it is one thing to understand that the Milky Way is only one galaxy among roughly 2 trillion in the observable universe, and another to ask what that implies for life, for consciousness, and for the presence of observers capable of recognizing that scale in the first place. The numbers alone suggest that the conditions for life should not be unique, given that there are hundreds of billions of stars in our galaxy, and likely far more planets than stars, and that this pattern repeats across an enormous number of galaxies. But the absence of clear evidence for other intelligent civilizations, often framed as the Fermi paradox, introduces a tension between statistical expectation and observational reality that has not yet been resolved. One possible explanation is that life itself, while chemically plausible, may be rare in practice, requiring a combination of conditions that are not easily met, such as long-term environmental stability, the presence of heavy elements, and protection from catastrophic events like nearby supernovae or intense radiation from active galactic nuclei. Another possibility is that simple life may be relatively common, while complex or intelligent life is far less likely to emerge. Or that civilizations capable of communication may exist only briefly on cosmic timescales, appearing and disappearing without overlapping with one another in a way that would allow contact. There is also the constraint imposed by distance, because even within a single galaxy, signals traveling at the speed of light would require tens of thousands of years to cross from one side to the other. And between galaxies, the time scales extend into millions or billions of years, effectively isolating regions of space, even if they are not empty. Within this context, the Milky Way takes on a different kind of importance, not because of its size or its position within larger structures, but because it is the environment in which at least one instance of conscious life has emerged. A system capable of producing not only stars and planets, but observers who can reflect on their own existence and attempt to understand the universe that contains them. This does not elevate the galaxy in any physical hierarchy, and it does not place it at the center of any cosmic structure. But it does introduce a distinction that is not captured by measurements of mass or scale, because consciousness is not evenly distributed in the same way matter is, and its presence, as far as current evidence indicates, is at least uncommon. At the same time, the recognition of scale has a particular effect on how meaning is interpreted. The vastness of the universe can be seen as diminishing in the sense that individual lives occupy an extremely small fraction of space and time, but it can also be seen as contextual, providing a framework in which local events gain clarity precisely because they occur within such an expansive background. Every human experience takes place on a single planet orbiting one star within one galaxy, and yet that does not reduce the internal significance of those experiences, because meaning is not derived from spatial extent alone, but from the processes that occur within a given system, including perception, memory, and interaction. The Milky Way, when viewed purely as a physical object, is one instance among many, neither the largest nor the most unusual, embedded within structures that extend far beyond its boundaries. But when considered as the environment that has produced at least one self-aware species capable of investigating those structures, it represents a specific condition rather than a general one, a location where matter has organized itself in a way that allows for the study of matter itself. This does not resolve the question of whether similar processes are occurring elsewhere, nor does it assign a universal significance to our particular situation. But it does establish a relationship between scale and awareness that is not captured by size alone. In that sense, the apparent contradiction between insignificance and importance does not need to be resolved by choosing one over the other, because both descriptions apply at different levels of analysis, and understanding that distinction is part of what it means to interpret the universe accurately without projecting assumptions onto it that are not supported by observation.